So for number 14, it wants us to find at least 10 partial sums of the series. So I've put this table where we begin at n is equal to 2, and we're going to go from 2 all the way out to 11 because that's 10 terms. And so an, so a2 is going to be 1 over 2 times 2 plus 2, so 1 over 8. a3 would be 1 over 3 times 3 plus 2, so that would be 15, 1 over 15. And then we go 1 over 24, 1 over 35, and so on, until we have 1 over 11 times 13, which is 1 over 143. So that is our sequence, and then we have our sum. So the sum of the first term is just the 0.125. The sum of the second term would be these two for n is equal to 2 and n is equal to 3. The sum for the first three terms would be of n is equal to 2, 3, and 4, and so on and so forth. So we're summing up all these terms from n is equal to 2 all the way out to n is equal to 11. So once we have done that, it is asking us to graph both the sequence of terms and the sequence of partial terms on the same screen. So we're going to go ahead and we're going to do this. Like so, and our sum, it begins at n is equal to 2. So this is going to be at 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Okay, and we're going to color code these. So I'm going to say that the yellow here, the yellow is going to be my an, and the blue is going to be my sum. S of n. Okay, so let's begin with the yellow. For n is equal to 2, and actually I should put some scale here. So maybe I should put that this is 0.1, that is 0.2, and then we have 0.3 and 0.4. Okay, so now that we have that scale, A1 is going to be 0.125, so it's going to be roughly here. And then A3 is going to be, let's see, 0.066. So that is going to be roughly here. And then we're going to have 0.04, which is about here, 0.02, then 0.02 again, but slightly less, 0.15, and then we get so close, 0.01, that it's basically going to touch here 0. So all these are very, very small. So that's our AN. And now let's plot in our SN. So the first one is also begins at the same point, which is 0.125. And then it goes 0.191, which is about here. And then 0.233, so maybe here. Then 0.26, which is about like so. 0.28. And then we have 0.29. Then 0.311. 0.32. 0.32 again. And lastly, we have 0.33. Maybe would be here. Yeah. So even though my drawing is not too great, we can see here that the sum definitely appears to converge, right? And the reason that it appears to converge is because each term, the further and further that we go, they get smaller and smaller. So the more terms that we add, those terms are going to be so small that it's basically going to be like adding 0. So it does appear that this series converges, but we do have to check it, right? So what we're going to do here is we're going to develop this mathematically, and we're going to turn it into a telescoping series. And so a telescoping series, it's a series where the terms cancel out. And the only way for the terms to cancel out is if you have something like 1 over a, instead of using a, I should use x or n. 1 over n minus 1 over n plus 1, or something of the sort, right? So for us to have a telescoping series, we need to have two fractions. And so we do need to decompose this stuff here into fractions, which is what we're going to do. We're going to say that 1 over n times n plus 2 is going to be equal to a over n plus b over n plus 2. So we want to just decompose these, right? And then when we decompose this, when we join these fractions here, what we're going to get is, if we want to join them into a single denominator, we're going to get a n plus 2 plus b n all over n times n plus 2. All this is equal to 1 over n times n plus 2. Okay, so our whole idea is that we want to decompose it into two partial fractions, right? And so when we join this, the partial fractions that were decomposed, we should get back to the same thing. So what we can see here is that the denominator is equal, right? So we don't need to worry about that. We only need to make the numerator equal. So we have here that a n plus 2 plus b n, that is going to be equal to 1. So let's try to find the value of a and the value of b. Well, this is supposed to hold for any value of n that you plug in. So what we're going to do is we're going to try if n is equal to 0. Well, if n is equal to 0, we're going to have a times 0 plus 2 is just 2, plus b times 0, that disappears, is equal to 1. Therefore, we have that a is equal to, if we divide both sides, a is equal to 1/2. Okay. Now, let's see if, because we want to make now the a term disappear. So we're going to say if n is equal to -2, we're going to have here a times -2 plus 2, so 0, right? That disappears. And then we're going to have b times -2 is equal to 1. And so from this, we can say that if we divide both sides by 1/2, that b is equal to -1/2. And so we can say, therefore, we have that the sum from n is equal to 2 to infinity of 1 over n times n plus 2 is equal to the sum from n is equal to 2 all the way out to infinity of a is 1/2, so we have that 1/2 times 1 over n, and then b is -1/2, so minus 1/2 times 1 over n plus 2. Okay, so once we have this, we can just clean it up. So what I'm going to do is just factor out the 1/2. So this is the same thing as n is equal to 2 to infinity of 1/2. I'm going to factor that out, and so that gives us 1 over n minus 1 over n plus 2. Okay, so now that we have turned our series into a telescoping series, let's take this expression over here and evaluate it for a few terms. So we begin, I'm still going to factor out the 1/2. So we go 1/2. If n is equal to 2, we have 1 over 2 minus 1 over 2 plus 2. That is going to give us minus 1 over 4. And then plus 1 over 3. So that gives us 1 over 3. And then minus 1 over 3 plus 2. So minus 1/5. And then we have plus, when n is equal to 4, plus 1/4, and then minus 1 over 4 plus 2, that would be minus 1/6. And then let's see, plus, if n is equal to 5, 1 over 5, minus 1 over 5 plus 2, which is 1 over 7, and so on and so forth. Now, the important thing to notice is that they come in pairs, right? Because our series, it's going to have two terms. So they're going to be paired like this. Right. So maybe I should expand and say that S of n, so the sum is going to be equal to 1/2 times all of this stuff, and it's going to go on forever. But now we notice something interesting, right? What do we notice? Well, we notice that this minus 1/4 is going to be canceled out with this plus 1/4. And this, let's see, this minus 1/5 is going to be canceled out with this 1/5, right? And so in this expansion here, we have this would be n is equal to 2, this is n is equal to 3, this is n is equal to 4, and this is n is equal to 5. So at n is equal to 5, let's see what was left. Well, we had the 1/2, right? And we have the 1/3, and the reason that these are going to stay is because it begins subtracting at 1/4. So there's nothing that's going to subtract 1/2, right? Because it goes minus 1/4, minus 1/5, minus 1/6. So nothing's going to get rid of that 1/2 and that 1/3. That 1/4 is going to be canceled out. That 1/5 is going to be canceled out. And then we're left with minus 1/6 and minus 1/7. And that is if n is equal to 5, right? If n is equal to 6, then some of these previous terms would get canceled out. So if n is equal to 5, what is our S of n? Well, our S of n is going to be 1/2 times that 1/2 stays plus 1/3 that stays, that's never going to go away, and then minus 1. Well, our n was 5, right? We evaluated this all the way to 5, so minus 1 over n plus 1, because 6 is n plus 1, and then minus 1/7, minus 1 over n plus 2, because if we're at n is equal to 5, the last term is going to be 1 over n plus 2, which is 7, right? And so this is our sum, because the more terms that we add, they're going to keep canceling out. So now that we have an expression for our sum, we need to take the limit as n approaches infinity of S of n. And when we take this limit, what do we get? We get 1/2 times the limit, that's 1/2, it never goes away, plus 1/3, that never goes away, and then minus 1 divided by infinity. Well, 1 divided by infinity plus 1 is just 0, so minus 0. And then similarly, we get 1 divided by infinity, so that's going to be minus 0 again. And so we have that this limit here is going to be, let's see, 1/2 times 1/2 plus 1/3 is 5 over 6. And then this gives us, let's see, 5 over 12, which is approximately, let's see what that is equal to. It's approximately 0.417. And so we can see that this is going to be our sum. And if we look here at our table, it does appear to get closer and closer. It does increase, right? But it does look graphically that the limit is going to be close to this last value, which is 0.33. And so we can see here that 0.41 is actually pretty close to that. And so that is it for number 14. So as a reminder, to find the limit, we just turn this into a telescoping series by using partial fraction decomposition. And then we saw how the sum cancels out, and we found the limit.